So thanks. Let us continue. Let me give a plan for today. So first we'll complete the yesterday program. And then we'll start with the step outside the standard Lie theory. So let me say that this is a notion of depth and gradient, PBW. And then I'll say what is the representation side of the story. Then I'll pass to the geometry. And finally, I'll say something about, well, coordinate rings and combinatorics of the coordinates. So this is actually similar to what we did yesterday, but as I said, so this is going to be a step outside. So this kind of today's lecture is a connection from between the classical side and outside the Lie theory. Okay, so first of all, what we did yesterday, so we started with some classical stuff, so classical Lie theory. So in particular, we defined irreducible representations of G, which is SLN for us. And we also defined flag varieties. In particular, an important point is that they sit inside the projective space of the lambda. And they depend only on the support, so not actually on lambda itself. Using the classical Cartan embedding, we saw that, so let's just look at the full flag variety for lambda having the full support. So the flag variety Fn, which is F omega 1 plus omega n minus 1, sits inside the product of Grassmannians, k from 1 to n minus 1, k of v omega 1. So this v omega 1 is the fundamental vector representation of our SLN, so n-dimensional. And we've fixed basis v1, vn. So this is standard basis of v omega 1. Right? And also we defined delta i's, Lucas coordinates. So these are dual to VI, VI, which is VI1 wedge VIK. I is exactly the collection of numbers I1 up to I. Okay. And so what we see is that this Fn sitting there can be described as a multi-projective spectrum of certain algebra. So more precisely, so Fn is the set of zeros of certain ideal. So this is a multi-homogeneous ideal inside the polynomial ring in our variable delta I. So this I ranges over all possible. So I is collection I1 of k, and k is any number from 1 to n minus 1. So you see, this is a huge polynomial ring, and we are saying that this is multi-homogeneous, meaning that so we are living inside the product of Grassmannians, and these Grassmannians are sitting inside the product of projective spaces lambda k of V omega. So since this is a subvariety inside the product of projective spaces, so our ideal has to be multi-homogeneous, so homogeneous with respect to all of them. So let me give you an example. So N is 3, and then our variety F3 sits inside P of V omega 1 times P of lambda 2 of V omega 1. So actually, this is a three-dimensional space, and the second Wedge power is also a three-dimensional space. So this is the product of two P2s, just two-dimensional projective spaces. And here we have coordinates delta 1, delta 2, delta 3, and here we have coordinates delta 1, 2, delta 1, 3, delta 2, 3. And I is actually generated by the single polynomial, which is delta 1, delta 2, 3, minus delta 2, delta 1, 3, plus delta 3, delta 1. Okay, so of course, in general, this is not the case. I mean, it's not always generated by a single polynomial, but you can give a collection of polynomials generating this ideal. And you see here, it's this polynomial is multi-homogeneous. The degree with respect to variables with one index is 1. The degree with respect to the variables with two indices is also 1. So this is fine. So it defines some sub-variety inside the product of two projective spaces, and this is exactly our subvariety. And the Plucker algebra, also called the homogeneous coordinate ring or multi-homogeneous coordinate ring, is defined as, let me write it as the Plucker algebra. This is the quotient of our polynomial ring written there. Overall I modulo the ideal I. Okay, and since our ideal is multi-homogeneous, so it has grading with respect to each set of variables corresponding to all possible k's given here. So we have a decomposition, the direct sum over M1, Mn minus 1 greater than 0. Here, this is the Plucker algebra M. So let me say that M is this collection. Okay, so what is actually this part? So this Plucker N of M is spanned by all monomials in variables delta I having total degree mk in variables delta I with the cardinality of A being exactly 2. Okay, so of course, this is the quotient of the polynomial ring, so it is spanned by all possible monomials in delta I. So let us just take those which have M1 variables of the form delta I with the cardinality of A being 1, M2 with cardinality of I being 2, and so on. So there is such a decomposition, and let me repeat that this is due to the fact that I is multi-homogeneous. So we can ask, what's that? And actually, the theorem or observation or whatever, so the claim, one of the basic effects in this geometric picture is that this space is isomorphic to the M1 omega 1 plus Mn minus 1 omega n minus 1, and we have to put dual if we want to say that this is an isomorphism as SLN. Okay, so the idea is just that we have an algebraic variety, which is our flag variety, and then it is realized as a subset inside the product of Grassmannians and inside the product of projective spaces. and we're getting this dual space as just a component of the homogeneous coordinate ring of our variety. Okay, so actually this claim has different sides. So there is this the celebrated Borel-Weil-Bott theorem saying that actually there is a family of line bundles on the flag variety, and then you can take sections of hierarchy homology, and then hierarchy homology vanish, and the sections produce these spaces. But this is not important for us for today. Just want to say that there are many approaches to this, and there are many ways to prove this. We'll do it. So just let me say that there is a way which is important for us, and just let me elaborate on that. How one shows that. So we will use the, for us, the important thing is going to be the following way. So first produce, so give a precise form of loop correlations. So these are relations generating the ideal. So this is an example of such a loop correlation. We'll have more examples later, but this is of that form. And second, give a basis of the Blücher algebra. And then just combine them together to be able to control the size of the ring and the structure of the ring, and so to see how these components look. Okay? So I'm not going to formulate these Blücher relations since we don't need them now, but instead let me say a few things about this basis, since this is a kind of combinatorial counterpart of the story, and there are many nice statements and nice constructions here. Let me just say that formulate one, which is familiar, I'm sure, for most of you. So this is the basis labeled by semi-standard tableau. So the idea is to give a basis. So we'd like to have as simple basis as possible. So how can we do it? So we can just take monomials of the form say delta. Let me write it like this: product delta I to the power Si overall I. So this is a kind of simplest element in this polynomial ring. You just take all possible variables you have, you raise these variables to some powers, some non-negative integers, Si, and then you get an element there. Of course, this is a class of this in the quotient, so we're not in the polynomial ring itself, but in the quotient, so we have to be kind of clever enough to choose these exponents in order to get a basis, right? So the question is how to choose Si to ensure that we produce a basis. And the answer is given by the following idea. So this has to be a semi-standard tableau. So in which sense? So tableau, so we have T. So first of all, we need to fix a shape. So shape lambda, which is M1 M n minus 1. Okay, so how do we do? So we take n1 elements, n1 boxes here. We just take strip. Yes, we have n1 times M1 boxes. And then we have M2 R, which consists of columns of I2, M2, and up to the columns of height n minus 1. Okay, so here we have n minus 1, and here we have m n minus 1. So we're getting a Young tableau, okay? And then what we do, we put numbers here. So elements, so this is T, and then I put T, I, J, so these are entries. So I is, so J is the number of column, and I is the number of a row. And these Tij are from the set from 1 to. Okay, so why do I want that? Just because I want to label my basis elements by such tableau in a very simple way. So I just say that so there is a requirement that the numbers Tij increase strictly. From top to bottom. Just let me put sign here. So, well, maybe I give you an example right away. Example like 1, 4, 6. So this could be a column. And to such a column, I attach delta 1, 4, 6. Okay, so this just columns correspond to my Plucker variables. And another thing is that numbers Tij non-strictly increase from left to right. Okay, so an example of such a tableau. So let me list, for example, so n is 3, and say lambda is omega 1 plus omega 2. So meaning that m1 and m2, 1. So what are my tableau? So they have shape the following form, right? So I have one column of height 1, one column of height 2. So I should, so the dimension of V omega 1 plus V omega 2. So you remember that for SL3, this is just the joint representation. So it's SL3 itself. So it's 8. So we need 8 tableau. 1, 1, 1, 2, 1. And then 1, 2, 2. And 1, 2, 3. 1, 3, 1. 1, 3, 2. 1, 2, 3. And the last variant for the first column is 2, 3. I can't put 1 here. I should put 2 or 3. Okay, so these are 8 semi-standard tableau. And of course, the theorem, let me put it here, monomials corresponding to semi-standard tableau form a basis of my Plucker. Okay, so let me repeat that this is an interesting combinatorial construction, but for us there is a direct connection to the geometry, so it allows to describe the coordinate ring, and so also gives some combinatorial model for the representations. Okay, so I'm done here. So any questions about the classical story? Yeah. So what do I do? So you see, these variables are kind of separated. So it means that these are responsible for this P2, and these are responsible to this P2. So I'm not kind of combining them together into P5, but I'm just saying that they kind of live apart. So this is important because our ideal is multi-homogeneous, and so they kind of do not talk to each other. So they have different degrees. Uh-huh. So kind of we need to, so suppose we are interested in this algebra, right? And we want to say what are the components of this algebra, right? For this, we need to say what are the relations and to prove that these are the defining relations. After that, we can do something with this algebra, somehow looking at the action of the Lie algebra or Lie group or something of this sort. So the basis helps to prove that the Pluk relations are indeed the defining relations. So you are giving some concrete ideal. So you are checking that this ideal indeed vanishes on the algebra, or on the variety we're interested in. And then you need to prove that there are no other relations for that. And this combinatorial structure helps to show that after you quotient out, this is exactly what you need. So we prove that these are linear independent in the quotient. Some more questions? Okay, if not, let us continue with the, yeah, sure. Absolutely, yeah. That's right. Right, but let's check. So this is of dimension 2, P2, and this is also dimension 2. So we're getting dimension 4 totally. And then you quotient out by one relation, we're getting dimension 3. So you see, this is important that we are not living in the space P5, but in P2 times P2. Okay? Absolutely. So let me be more careful. So what I want to say that, so we have degree of each delta I, with I being I1 ik is 0, 0, 1, 0, 0. So this is the kth place. And then I'm saying that this is a kind of multi-degree thing, right? So this is not a projective embedding, but multi-projective embedding. Yeah, you're absolutely right. So one has to be careful here. This is not the standard kind of situation where we describe projective variety right inside the projective space, but rather we separate it into several parts. So to make it more precise, I should write the product of several polynomial rings, and then they have degrees this form. Right? Yes. So here I'm working with the weight with the maximal possible support, but in principle, the support can be. So I mean, so I said that lambda is omega 1 plus omega n minus 1, but what's important that the support is the full set of nodes. So if it's smaller, I just say that there are no columns of some fixed height. So I'm saying that I'm restricting to some heights which correspond to the support of my node. So this semi-standard tableau, they exist for any weight, not necessarily regular. That's true. So when we are so when we are talking about this case. So the nice thing is this embedding into Grassmannian. But if we say put here twice, so on. So in principle, the embedding changes. But we are saying that anyway, so this is sitting inside the product of Grassmannians, and they sit in here. So if we want to be kind of more kind of in the realm of these line bundles, so this is important because then the inverse image of the line bundle of this projective space for the kind of different embedding gives you another line bundle. But on our level, it's not important because we are just saying that in any case, this is Grassmannian, and we are looking at the simplest possible embedding. So this is just to simplify. Yeah? Sorry, say it again. Uh-huh. So you see, how to say, so let me see, work out here, right? For example, if I have, say, M1 is 2 and M2 is 3, so then an element which I'm kind of interested in is something like delta 1, delta, say, 2 times, say, delta 1, 2 squared, delta 2, 3. So you see, I here have two variables with having one index. Say it again. Absolutely, right, because you see, I'm living in this. So we are lucky, right? So you see, we are lucky that we have ideal generated by this very simple polynomial. But of course, if you generate ideal by this polynomial, so you multiply it by any polynomials you have, so you might get any powers here, right? But in general, the ideal is quadratic, and it always, all the generators, they look like this pattern, so meaning that you have quadratic expressions which are linear in all the things, but when you generate, you're getting much more complex. More questions? Okay, then let's move on. So we want to consider some extra structure at our representations, and let us ask very, very innocently looking question. You remember we were discussing the irreducible representations V lambda, and one of the important properties of these representations is that we take u of n minus and apply it to the high state vector, right? So it means that our n minus is spanned by Fij's. So these are matrix units corresponding to the lower triangular subalgebra. So Fij between 1 and n minus 1. And we apply all possible Fij's, all possible matrix units to get from the high state vector to everywhere. And we can ask the following question. So how deep is a given vector a vector in V lambda locate. So what does it mean deep? Deep means that, okay, so we start with V lambda. So this is our starting point. And then we apply, say, all possible Fij's to V lambda. So let me write again. So this is a new set of vectors. And we need only one step to get from the top to these vectors. Okay, so just apply your operator once, any of those, and then you get it. And this is some subspace. But then, of course, there might be not, this doesn't have to be the whole space. So we might need to apply once more. So F, say, I1, J1, I2, J2, V lambda, and so Actually, in my notation, so this is less than or equal because I choose here to be n minus 1, right? So for example, let me maybe write an example. So say n is 3, then f11 is, so it corresponds to the first simple root, and then f22 is 0, 0, 0, 1, 0, and f12 is 0, 0, 0, 0, 0, 1. So this notation comes from that this guy is actually f alpha 1, this guy is f alpha 2, and this guy is f alpha 1 alpha. Okay, so it means that we are getting kind of larger and larger space, provided that we are allowing ourselves to somehow use more operators, right? So we go deeper, deeper, and deeper. So let us just formalize this. So the definition. We define PBW filtration. So Fs inside P lambda. So this increasing filtration. So of course, it's actually finite because so at some point we're getting the whole V lambda. And then by definition, Fs is the span of the vectors of the form Fi1, J1, Fi, say, R, Jr, V lambda, R less or equal than S. So you see, this is a kind of not something new because so if you are proving the PBW theorem relating the universal developing algebra to the symmetric algebra, this is how you do it. So I mean, you introduce this filtration, and then you see how things work. And so we just kind of induce this standard PBW filtration on the universal developing algebra to the representation space. And the main object, so we want somehow to discuss, to describe, and to study is the graded space. So this is a direct sum over S greater than or equal to 0, F S over F S minus 1. So this is the graded space of Milen. So for S equals 0, of course, F0 is nothing but the span of the highest rate vector. This is one-dimensional, and we don't have to divide over F minus 1 because there's no F minus 1 here. So it starts with F0, and then you go further, further, and further. So let me give you an example, or maybe even several examples, just to illustrate how it works. So the simplest possible example is, say lambda is omega 1, just a fundamental weight. And then the situation is as simple as possible because we start with, so our V omega 1, just a span of V1 up to Vn. And so F0 is the span of V1. So this is just the highest rate vector, so the cyclic vector. And then F1 is already everything because, of course, you can move to any basis vector starting from V1, just applying the matrix unit, which sends 1 to whatever you want. So here, this graded V omega 1 is just, well, span of V0 plus span of Vk, k greater than 6. So the situation is very simple here. Let us do a bit more complicated example for other fundamental weights, k greater than 1. So let's see how it works here. So we again start with F0, which is just the span of V, yeah, maybe, right? At V omega k is lambda k of V omega 1, and V lambda is V1 verge Vk. Now, F0 is the span of V1 verge Vk. So this is our high state vector, and we have nothing more at the 0 space. Now, suppose we want to do the first step, apply our operators 1. So what do our operators do? So our operators are from lower triangular part, right? So what you can do, you can take a vector and then make it index larger, right? So this is a lower triangular part. Okay, so you can take our algebra acts on these vectors. So it just takes any vector from here and makes it index larger. So of course we are not interested in indices which are from 1 to k, so they're all here. So we can move one index outside. Okay, so F1 is the span of vectors of the form V1. So then we skip V I. And we replace this Vi by some Vj, where j is larger than k. Okay. So just take out one vector and then add another vector. One vector is from the first part and another from the remaining part. Absolutely. So plus F0. So it has to be an increasing filtration. So we add everything we got in the previous step. Okay, so in general, Fs is the span of vectors of the form Vi1 verge Vik, such that the cardinality of my I, so you remember I is the set of these indices, I1, Ik, intersected with the set k plus 1 n is at most S. Okay, so we're just looking at those verge products such that you have no more than a given number of vectors from the kind of larger part of the set. So which are k plus 1 up to n. Okay. So these cases are very simple. So you can be worked out by hand. So let me maybe add one more example, which is kind of less trivial. So n is 3, SL3, and omega is lambda1 plus lambda2. So you are probably seen somewhere such a picture. So this is a picture of sorry? Oh, thank you very much. Yes, lambda is omega1 plus omega2. And so this is the standard picture of the adjoint representation for SL3. So it's a-dimensional. So this is the high state vector, d lambda. And so this is our F0. So we start with F0. And then we can act by our three operators, F11, F2, 1, 2. And we are getting a 3-dimensional, actually 4-dimensional F1. So this 3 plus 1. And then F2 is already everything. So you can get any vector by applying your operators. Good. So this was the idea, and this is part 1 of the story. And now okay, so this is fun and nice, but is there some structure? And there are many. So let us start developing the theory, so representations. So of course, we've started with V lambda, and V lambda is not only vector space, but it is a representation, right? So there is a Lie algebra SLN acting there. So we might and we should ask what is the induced structure? How do the operators, what do the operators from SLN induce here? And then let's put the first lemma. Saying that the operators Fij induce commuting family on Milen. Okay, so the claim is actually very simple, but kind of crucial. So namely, what we know is that Fij maps Fs to Fs plus 1. Right, by the very definition, if you Fs is a span of all vectors such that there are no more than S operators applied to the highest weight vector. Now Fs plus 1, we should add no more than 1. So we are doing that. So there is this map, and therefore we have the induced map Fij from Fs over Fs minus 1 to Fs plus 1 over S. Okay. So we can easily say what are those maps. So we take a non-zero vector in this quotient, so just a class. Then we apply Fij to this guy, and it is in Fs plus 1, but could be also in here. So if it is in here, then the result is 0. Otherwise, you're getting something new. And the claim is that so the induced operators Fij from on Vyjayanthi, they commute. And actually, it's very easy to see because we know that the commutator Fij with I1, J1, I2, J2 is again a linear combination of Fij's. Okay, because this is a Lie subalgebra, so this is a yeah. Right? Absolutely. Yeah. This is exactly what's written. Yeah. Absolutely. Yeah. Yeah. So this linear combination of Fij, so it means that if you apply Fi1 J1, Fi2 J2 minus Fi2 J2, Fi1 J1, and you apply it to Fs, then the result is in Fs plus 2. Okay, not in Fs plus 2. So it's 0 in the. Okay, so the conclusion is that we have an algebra, which let me denote by n minus a. So this is abelianization, abelianization of n minus. So meaning that, well, this is the same vector space with the same basis Fij, but there is no bracket. Bracket is 2. And we see that this algebra does act there, and actually even more that our graded V lambda, which I maybe for brevity will denote by V lambda A for abelian, is just the polynomial algebra in Fij's, overall Ij's, over the some ideal. So I mean, these guys, they generate the whole space from the high state vector. Well, there is some vanishing ideal, but now it's kind of simpler. So this is just the polynomial, not the complicated universal developing algebra, just the polynomial. So this is this part. And actually, let me also note, so this is not going to be very important for us, but still remark, says that Borel, which is now positive Borel, so this is a complementary to n minus. So if we apply Borel to Fs, we are still in Fs. So this is not, this is simple, but not maybe absolutely obvious. So the claim says that if you take a product of this form, and then you apply here an element from the upper triangular part, then you can move it to the right. using the commutation relations. And then the Borel part either kills or stabilizes V lambda, then, well, on the way you're getting something, but this something never longer than X. And therefore, this remark implies that B acts on V lambda. Moreover, B applied to Fs over Fs minus 1 is inside Fs over. So we have a grading on this V lambda, right? Just grading corresponding to this S. And then the action of n minus 1 increases this grading by 1, and the action of B preserves this grading. Okay? So let me kind of give you the definition. So we can ask what is the Lie algebra formed by this n minus a and b, and the definition is that, so let SLN A, so this is a kind of degenerate algebra. So this is the direct sum n minus a plus b. So this is the direct sum of vector spaces. So as a vector space, so we have abelian part. So you remember n minus 1 was and is a lower triangular algebra. So instead of looking at the non-commutative, we replace it with the commutative algebra. And then we are left with the upper triangular part, which is non-commutative and still is non-commutative in this new algebra. So this is subalgebra. And actually, this is also subalgebra, but also, in fact, an ideal in SLN-A, abelian ideal. So abelian ideal means that if we commute an element from here with an element from here, we should stay inside. So this is not true for matrices, right? So you, in principle, if you take lower triangular matrix and upper triangular matrix, you commute, you can get upper or lower, diagonal, whatever you want. But here we say that we are still here, and then the structure is that we say that this n minus a is isomorphic to SLN mod B, right, as a vector space. Okay, so this is B module, this is B module, we take the quotient, and this is the action on this n minus. So, so this gives the B module structure. So in words, what do you do? So you take an element from here. So this is a lower triangular matrix. And then you want to commute it with the upper triangular matrix, right? So you do it as you do in the real world, yeah, in the usual settings. But you might get something which is upper triangular or diagonal, just throw it away. Okay. This is the algebra. And then the claim is actually that this algebra acts on this V lambda. So this, the outcome let me state it as not the proposition. So V lambda is an SLN right, yeah. So it's direct sum of B, right, which is just the usual, and abelian. Okay, so the algebra becomes maybe not that nice as before, but this is exactly what we want to describe this graded. Okay. So of course now there are many questions. For example, so what is the dimension of Fs over Fs minus 1? So what is the character? So what is the maybe some basis for or this graded space. So you see, this is a kind of refinement of the classical questions in the Lie theory. So if you want somehow to compute the dimension of the whole space, you may want first to compute some parts of that and then sum up, or some basis or whatever. So I'm not going to answer these questions. Just want to say that we started with a very classical thing, and we introduced some extra structure. And then let's see what other pieces of the structure are there. Okay, so this is this second part on the representations. Now, of course, as always, so if you're asking some algebraic questions, you better see some geometric picture behind. So let us try to, sure. Yes, sure. So for example, sorry, the answer is no. For type A and for type C, but not in general. Yeah, in general it's not no. So by the way, I have more space here. Yes, so one implication is that, so suppose we want to have a basis for this. So what kind of basis can we have? So for example, we have an action of operators F alpha, which are Fij's for us, right? So they act on the high state vector and then generate something in this graded space. So if you have a basis for this graded V lambda, you have a basis for the classical V lambda itself. So for example, there is a very natural classical question how to give a basis in the representation space of a SLN or arbitrary G, right? And then, well, there are crystal bases, some other bases, but the most natural question is, so you start with the high state vector, you start applying your F alphas. So what F alphas you have to apply to get a basis? And in general, I don't know an answer to this question for general G. So, but here there is an answer. So you just say what, so you take the product, say Fij's to the power Fij's. So just here you see the order is not important. So just what are the powers Fij you have to take in order to give a basis? It's one of them. Another thing is I'm going to say in a minute, so it's more geometric, but you have the flag variety, and then what you can do this is flag variety. Can you somehow degenerate it, change it? So consider some more structures on that, and it's going to show up in a minute. So kind of this is a new object. This object comes from the classical Lie theory. The claim, which we'll see later, is that you can degenerate a classical object, just consider a family containing as a special fiber this new thing, and as a general fiber the classical things. And if you know something about the special fiber, you can get information about it. Yes. But not in general. Right, so so far there's no family here, right? I just defined just one thing starting from the classical representation. But what I'm saying, and I'll try to explain it later, that actually there is a family, maybe draw a picture. So this is not, so there is a way to get it just as a single construction, so just as a single procedure. But what you can do, you can take A1, so just line, and then you can take 0, so you can consider a family which consists of V lambda at any non-zero point. And then, so there's a procedure which somehow changes or degenerates classical V lambda to this graded version. And I hope we'll see it in the geometric side as well. But some more questions? Okay, so let us move further. So with the geometric part. So actually, you can guess what is the object, because we are following the same strategy. So you remember our flag variety F lambda is the closure of n minus applied to the line V lambda inside P of V lambda. Okay. So this is the variety. So of course, in this classical situation, we don't need to close because we have G. We can apply G, and this is the orbit closure. We had all this discussion yesterday. So after all, we have three descriptions. So either as such a closure, or as one orbit, or as explicitly given subset in the product of Grassmannians. Okay. Now we putting forward the following definition. So our abelian version of F lambda A is the closure of the, let me put this n minus A, the moment, and it would be lambda. And then this has to sit inside P of V lambda A, which is just the gradient of V lambda. And this n minus A is the exponent of n minus A. So just the Lie group of the Lie algebra n minus A. But you see this, actually the situation becomes simpler or more complicated, but on this level, this group is much simpler than the group of lower triangular matrices. You take abelian Lie algebra, you take the exponent, and what you're getting is just what is called GA. So GA is just the additive group, so just the group C with the iteration plus, right? Raised to the power n times n minus 1 over 2. Yeah, so which is the field, and you just take several copies of this, and this is your group. So what we are doing, we have some space. The abelian Lie algebra n minus a x here. So it generates the whole space from this V lambda. So actually, I denote this V lambda by the same symbol, but please note that this is now a vector in the graded space. So our F0 is spanned by this V lambda, but just not to overcomplicate the notation. So I use the same symbol to denote this vector. And I take this group and I get something. You mean this one and this one? They're very different because you see here, this group is not abelian, and it acts in the space V lambda. Here, a priori, we are doing absolutely different thing. So we are taking another space with the action of another group, which is now abelian, and we apply it to some vector. So a priori, so in particular, you see there is no action of the group n minus anymore. So it's not the same space. And so let me give you an example when. So the relation is that one is degeneration of another. So there is a family such that if you take this classical object as a special fiber, you can degenerate as a general fiber, can degenerate it into the special fiber given by this. So let me give you actually an example, and I'll stop. So there are some cases when these spaces, they do coincide. So maybe I give two examples and then I'll continue tomorrow. So one example is trivial. So if lambda is the fundamental weight, any fundamental weight, then F lambda A is still Grassmannian K, V omega 1, which is just the F lambda itself. So nothing changes here. I'll explain tomorrow why. And an interesting example that if, say, n is 3, and the lambda is omega 1 plus omega 2, So then f lambda a also sits inside P2 times P2. And you remember we had the defining relation here. So also f lambda sits here, but here the defining relation is delta 1, delta 2, 3 plus delta 3, delta 1, 2 equals 0. And here it is delta 1, delta 2, 3 minus delta 2, delta 1, 3 plus delta 3, delta 1, 2 equals 0. So what happens, you somehow erase this term, or you put your parameter here, and then in the limit it disappears. So let me stop now. Thank you very much.
Questions?
Yes. 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 So there is a procedure, so I'll say something tomorrow, but you can give explicitly given blue correlations and just generate them. In type A. In type A, and actually in type C.
Any more?
Variety remains irreducible and remains of the same dimension. So it is irreducible because it's the closure of this orbit, one orbit, so it has to be reducible. And by the same reason, it is of the same dimension. Actually, it is a flat degeneration, but we'll discuss. It is. There are several ways. So one way to say is to give a family over A1 such that the general fiber is the classical object, special fiber is this new object. So this is the first thing. Another thing is, as you're saying, so given an ideal, just give a kind of family of ideals, right? Just say where you put this kind of epsilon or parameter, what terms disappear. So there are several ways to say, but this is one. There is also combinatorial.
Okay, so if no more questions, let's thank the speaker again.